Voilà, nous allons écouter Bob Coecke qui va nous parler d'applications courantes de catégories monoïdales et de cutting edge techniques, voilà, en rapport avec l'intelligence artificielle et le calcul quantique.
I'm here. So let me share the screen.
Okay.
Enter full screen. That's all fine, I guess.
Yes.
Yes.
Okay. Okay, hello everybody. It's really a pleasure to be here. So I made my title a little bit shorter. It's now monoidal categories in quantum and AI industry and in education. It's really an honor to be speaking here because I've known Jean very long. In the picture you see here, that's in Oxford, I think approximately 10 years ago. And I'm not sure, but this may have been his last international trip. He was very happy for the week because he had never been in Oxford, he said before, so he enjoyed it a lot. Here you see.
Bob, we do not see a picture.
You don't
see? We do not see a picture. No, only your laptop, your desktop. Sorry.
I see. Wait, let me go back. Stop share. Share again. No, okay, now. Yeah, oh, sorry.
Yeah, now we see it.
I picked the wrong screen. That's what you get after 20 years of professor of computer science. Okay, view, enter full screen. Okay, so basically, you see the picture here, which is Jean, which maybe have been his last international trip. I mean, I'm not sure, somebody can tell me. This was in Oxford. This was his first time he was in Oxford. He spent the week with us and he had a lot of fun. So here you see him eating outside with Alex Kissinger, Jeffrey Morton, Jamie Vickery, Chris Heunen, and a little bit of myself. I mean, the first time I met him was probably on one of Francis Bourseul's retreat in the Ardennes in Belgium, because I'm Belgian. And then in, I think it was 99, together with Isar Stubbe, who's co-organizing this, we organized a conference, a workshop in Belgium, and also a PSSL. So for the workshop, we had some money, and we invited Jean Benabou and Jim Lambeck. It was a very light program, few talks, so we had a lot of fun together. It was very pleasant. And then in the weekend, we had like a very notorious PSSL, because the university didn't want to give us a room for free. We actually moved into a squatted swimming pool. The PSSL took place in the swimming pool itself. And then we built a big balloon around it to try to keep us warm, but it failed. And I mean, Lavere was there, Francis Bourseul was there, many people were there. And unfortunately, there's no photographic evidence. And if anybody has photographic evidence, please send it to us. Because if somebody was there who's now in the audience, please say so, that we have evidence that this thing actually ever happened. Anyway, so let me now go to the talk. I mean, to explain a little bit the story that I'm doing here, let me sort of say something about myself. So for a long time, I was a professor at Oxford University. I became full for some 13 years. But then, I mean, this was together with Samson Abramsky, and we built a very big group there, like doing a lot of applied category theory, some pure, some other things, but mostly like compositional stuff. In 2020, I resigned from my faculty position, and I joined a quantum computing company, Cambridge Quantum. Part of the reason was that a lot of the stuff we had been doing before was actually moving into industry with companies like IBM and Google. I'll say something more about that. But in 2021, that kind of stopped, because what happened is we as Cambridge Quantum, we merged with part of Honeywell. Honeywell, you may know from your radiators or your thermostats and stuff like that. So they actually had been building quantum computers, and that part of Honeywell then merged with us. And so it became Quantinuum. In Quantinuum, we now also have a team in Oxford. So there's actually now 2 large teams in Oxford, one in CS department, one in Quantinuum. We have our own offices there. So a lot of these people were before, of course, with me in Oxford, and some new ones. You may recognize Sean Marzit, bottom right, who's doing a sabbatical with us. And I also saw that Katerina Pucci, the lady with the yellow dress on the bottom, is here in the audience. So you can basically ask questions during the talk in the chat, and I think Katrina will be able to answer them. We also have we welcome sabbatical visitors, and we welcome PhD students and all that. Like I still got a lot of PhD students. I'm still affiliated with Oxford, of course. I'm still teaching in maths at Oxford. This is our logo of our local Oxford team. You can see I'm wearing this also as my t-shirt. Why am I saying this? Because, I mean, this is compositional intelligence. That's our way of saying artificial intelligence, because everything we do is based on composition and monoidal categories, which, of course, Ben Abour is the originator of. So the entire team is now doing like stuff in quantum and AI, starting from things like monoidal categories. So our brand is compositional intelligence, or quantum, because this also looks a bit like a Q. And I mean, the fact that it looks like a skull really has nothing to do with me. That's just very unfortunate, I should say. Okay, let me now start with the story. So, and this is all about the language of quantum. And this story starts with von Neumann. Von Neumann is the originator of the quantum mechanical formalism using Hilbert spaces and linear map and all that. And he published them in 1932 in his book. And then, very remarkably, in 1935, he basically denounced his own Hilbert space formalism. Like he says here, I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space no more. And then so on. And a large portion of von Neumann's work was basically coming up with a new quantum mechanical formalism. All his work towards von Neumann algebras and all these things was all motivated by coming up with a new quantum formalism. But arguably, while he invented a whole bunch of new fields of mathematics, these things never had any impact really on quantum theory and quantum community. Now, one thing von Neumann stressed very much was that in order to come up with new quantum formalism, you should first conceptually analyze the notion of measurement, and from that starting point, see what sort of new formalism should do. And his first thing was like, for example, with Gerrit Berghoff, something called quantum logic, but that's now completely vanished. Okay, here is Erwin Schrödinger. You probably all know from his cat and his equation. And Schrödinger had a very different idea than von Neumann. He basically says somewhere, I mean, I'm just going to paraphrase it, that composing quantum system, like doing composition of systems, is not one, but rather the characteristic trait of quantum mechanics. So he was emphasizing compositionality, composition of systems, like we do in a monoidal category, as like the main core ingredient of quantum mechanics. But of course, there were no monoidal categories around. So basically, nobody did anything with that because the mathematics didn't yet exist to actually realize a program like that. So everybody was just following von Neumann because that's that you could do with like traditional maths. And then in 2004, Samson Abramsky and I, we wrote this paper, Categorical Semantics of Quantum Protocols. And that was really, in hindsight, because I didn't even know about the Schrödinger paper because it was never really very prominent anywhere. But this was really realizing Schrödinger's view, like starting quantum mechanics from scratch, but now with composition, the first citizen. And of course, what did we use? We used monoidal categories, a la Ben Abour, and then some specific kind of monoidal categories, which were the complex closed categories of Max Kelly. So that's really what we used. It was very interesting. I didn't know about Kelly's complex closed categories, so I was messing about when we did this, and then at some point I bumped into it. Very hard to read for me because I didn't have a proper category theory background, but then we kind of realized, hey, that's exactly what we need. That's exactly what we need. The only thing we had to do was add a dagger. And a dagger is like an involution, and this allows you to account for like complex conjugation, which is really essential in quantum mechanics. So, but pretty much we could take compact closed categories off the shelf, like as they were. With the exception then of the dagger. Okay, so this is Roger Penrose, and Roger Penrose was drawing pictures like this. Now they're of course very famous in category theory community. They're called string diagrams, but at the time they weren't that prominent yet when Samson and I did these things. But I mean, one problem we had with our categorical semantics of quantum protocol and the whole program was that monoidal categories, in the way you found them in the literature, was really one bridge too far for most physicists to actually even bother to look into this thing. It was really one bridge too far. Now, maybe if we move to Penrose pictures, then we could sell things much easier. And of course, this was perfectly justified because by the work of André and Ross, we basically connected up Penrose's pictures to monoidal categories. And so then I wrote some sort of, this was not really a research paper. This was more like a programmatic paper called Kindergarten Quantum Mechanics, where I pretty much wrote the same thing as in the first paper with Samson, but we basically used only the language of string diagrams rather than monoidal category axiomatics. And the quest which I posed in that paper is, can we redo the entire quantum mechanical formalism pictorially? which of course is the same as entirely compositional, where everything, including quantum measurement and all the other stuff in quantum mechanics, complementarity, Heisenberg uncertainty, everything is formulated just in the language of monoidal categories or diagrams if you want to. Okay, so I mean, this is now very, very well known, like in category theory circles, like this yanking axiom or zigzag axiom, as John Byers calls it. So that was, of course, at the core of our quantum categorical semantics for quantum protocols paper. And then linear algebra actually becomes very simple. Like what you see here is just a cartoon indicating the transpose. So if you take a box which represents a morphism, and you wire the input into an output and the output into an input, then basically if you yank it, this is the equivalent of a transpose. So it shows that you can basically represent the transpose diagrammatically merely by 180-degree rotation. So that's all simple, but that doesn't give you full-blown quantum mechanics. These sort of things don't give you full-blown quantum mechanics yet. So we worked hard for many years, and then 13 years after this, with Alex Kissinger, we published this book, Picturing Quantum Processes. And this was really a full course of quantum computing, quantum foundations, all entirely in the language of monoidal categories, if you wish. Of course, in that diagrammatic presentation, because we needed to sell this stuff to the physicists. So anyway, so this is the course. This is the course which is started in Oxford Computer Science, quantum computing course for the past, I think now 8 years or 9 years or 10 years. So Alex Kissinger has pretty much taken over my role there. So it's all still going on. And it's been getting a lot of traction. And this book has really caused that people much more now start to use this formalism than the traditional Hilbert space formalism. I'll say more about that later. But still, like, I mean, to read this book, you really need a university. You need to be at university because we are responsible professionals. So if you're going to teach people quantum theory, then you should also teach Hilbert space. Otherwise, they can't read any paper out there. So, for example, what we do in this book is we start from diagrammatic quantum mechanics and then say how this becomes Hilbert space quantum mechanics and how they're related. So it's not so easy to read. Although, I mean, of course, I had this title, Kindergarten Quantum Mechanics, which indicated that we really wanted to make it broader than just than academic level. Okay, 5 years later, and this is a premiere. This is a premiere now because this cover is only finished since yesterday. This is like the final cover. The designers only finished it yesterday. So that's a new book, and it will be out in December. It will be out in December. So this is Quantum in Pictures. By Stefano Goggioso, who is now also faculty in the same group in Oxford, a former student of mine and myself. And this generally is a presentation of quantum theory with cutting-edge modern stuff, new results, which we didn't even know in the big book, but in a language which is understandable, we expect for teenagers and anybody with an interest to learn about quantum but doesn't have the math background. But of course, is quantum mechanics in terms of monoidal categories. This is what it is. Quantum mechanics in terms of monoidal categories for teenagers. So the category theory has actually enabled to make quantum, which is usually regarded as such a difficult subject, to make it much more inclusive than one probably would ever have imagined. so I mean, let's see how it gets perceived. Let's see how the book gets perceived. But I mean, we're very hopeful that we already did tests, of course, with teenagers reading this, and they really had no problem reading it. So we know this now. So of course, the big problem is teenagers don't read anymore. They just watch screens. So what we did also is we actually filmed the entire book. We filmed the entire book in my office here. This is in my office, and this will all become available on YouTube, of course. The book itself will be cheap. Because it's actually published by our company just to keep it cheap. Just to keep it cheap. We don't intend to make any profit with it. We just want to basically make it very, very accessible and create inclusivity, not just in the Western world, in also like third world, where it's much more difficult to actually pay for books and stuff like that. So we kept the price really down and all that. Okay, I'll take you a little bit through it. Now, what I'm going to do is basically in 2 minutes, go through 60 pages. So it's definitely, this is not the speed it's presented there, but I just want to give you like a sense of how things are inside of that book. So of course, it's a story of string diagrams, like it's wires and boxes. And the way you think about a wire, as we explained, that is, this is a place where quantum particles live. So they live in wires, just like electricity lives in electricity wires, and they can go through it. And then boxes are things, processes, if you want to, which act on these quantum particles. This. I mean, you can also think of the wires as well, like where food flows, if you want to, food flows, and then the box has a cooking recipes on food and stuff like that. I mean, everybody know this is now quite well spread in category theory. This view, I don't have to explain this. And then of course you can compose them because it's all about compositionality. So we got monoidal category, and then things become really interested, and this is now the compact closed category coming in. Things become really interesting when you start like drawing a trivial equation like this zigzag, well, not trivial, it's highly non-trivial, of course, an equation, but trivially looking equation like this yanking equation, and then interpret these cup-shaped and these cap-shaped wires as boxes as well. So you give them a name, pretty much, you give them a name. And the physicist would call the cup-shaped wire like a Bell state, or an EPR state, or an Einstein-Podolsky-Rosen state. So really heavy names. They're just cup-shaped wires, but they are the things for which this year, in 2022, the Nobel Prize Physics was given. It was given for the behavior of these cup-shaped wires, this year's Nobel Prize. That's really what it was about. So these are cup-shaped wires, and so they're entangled states. So the Nobel Prize was pretty much given for the existence of entanglement and resulting non-locality and all that. And so this is what this cup-shaped wire represents. It's really like Nobel Prize material. And then the cap-shaped wire is the dual. It's like the corresponding test or question. So the thing at the bottom is basically two particles in an entangled state, and the top is the question: are you two particles in an entangled state? So this suddenly becomes a non-trivial equation. And then you can do things like you can take your boxes and just slide them along these wires. And then on the hard upside down is the transpose of the hard on the left. And then without much effort, you should suddenly invent quantum teleportation. Without much effort, you suddenly invent quantum teleportation. So quantum teleportation is something that was invented in 60 years. 60 years after von Neumann published his quantum mechanical formalism in his book. It took 60 years, it took 6 people to discover. And here quantum teleportation can just be simply explained just with these wires and boxes. So basically, you got a badly drawn galaxy here. Now in the book, we've got nicer pictures of planets rather than galaxies, bad pictures of galaxies. So on one side of the galaxy, you got Alice. On the other side of the galaxy, you got Bob. They share a Bell state. They share an entangled pair, which means one particle is with Alice, the other particle is with Bob, and they're entangled. And then Alice at her side does this cap-shaped thing, which is basically asking a question. And then you see the box on the left, which is actually what Bob desires to have, can just be pushed along the wire to the other side. And that's really quantum teleportation. That's what it is. So that's really what was in our paper in 2004 at LIX, when we said you can reason quantum mechanical stuff, you can do quantum mechanical stuff with compact closed categories. That's really what was there. And then kindergarten quantum mechanics really had this example too, but if you want to do full-blown quantum mechanics, that's not enough. Wires are not enough. You can't just do this with compact closed categories. You need more. And what you need is what we call spiders. I'll later say what it actually is in category theory jargon. But we call these spiders because the following reason. So first to understand why we introduced the spider, or the way we think about it, and it's an easy sell. Okay, let me say. So these spiders are special Dagger commutative Frobenius algebra. I mean, that's not something you teach to teenagers. Hey, take a special Dagger commutative Frobenius algebra. You don't teach this to teenagers. They don't get what that means. So that's why you call them spiders. Okay, so this is a wire. So what is a wire? The wire is a thing with two endpoints. That's really what it is. A wire is a thing with two endpoints. Now, what can you do with wires? You can just connect them. And if you connect two wires, you get another wire. That's really the equations governing wires. That if you connect two wires, you get a new wire. Now with our spiders, so here is one, and then they're friendly spiders, they say hi. With our spiders, we have the same principle that when two spiders get connected, you get a new spider. The difference, of course, is that the number of legs may change, depending on the number of legs of the spiders and along how many legs they actually connect. Now, this looks like a silly equation, but if you think of, but this is really the main equation governing Frobenius algebras. This is the main equation governing Frobenius algebras a la Carboni-Walters. This is the main equation. And if you interpret this equation in Hilbert space, so saying the spiders are actually linear maps, the legs are, say, two-dimensional, or actually dimension doesn't really matter. The legs correspond to Hilbert spaces, and between the legs you got a tensor product, and you interpret these equations, then you can actually show that you're axiomatizing an orthonormal basis if you involve the dagger. If you involve the dagger, then you can show that this is an axiomatization of the notion of orthonormal basis, which is incredibly cool. And this orthonormal basis is like a key ingredient in quantum mechanics, which is necessary to basically say what a measurement is. So this equation is kind of axiomatizing measurement from composition. So quantum measurement from monoidal category language only. So this is, of course, a key part of this diagrammatic formalism we have. Now, one kind of spider is not enough. You really need two kinds of spiders, and then the equations governing them is, for example, this. I mean, they don't like each other, so you should really think of this as they sort of hit each other. The red spider hits the green one gives a punch to the red one, and they hit so hard that their legs fall off. So this is the equation. You got like a green dot connected with a red dot. There's two wires in between, and then they fall off. That's the equation. And this, again, corresponds to a very important concept in quantum mechanics. This is complementarity. So it's like the thing which exists between position and momentum, for example. So they all these heavy concepts get all these nice and light pictures now. Now I'm going to do something much more practical in quantum computing. So what you see here is a quantum circuit. And then you can, and I mentioned that the spiders correspond to orthonormal bases. And if you take two, for example, what's called the Z basis and the X basis for a qubit, for a two-dimensional Hilbert space, and you take these spiders, you get something which is called the C NOT gate, the controlled NOT gate. I mean, it's also something in classical logic gates, of course, but it's a very important one in quantum computing. And so whenever you see a red dot and a green dot connected by an horizontal wire, that's a C NOT gate. So what we really got here, so you have to think of the vertical wires as quantum particles, and then the gates acting on these quantum particles. That's the way you should think about this picture. And now quantum computers, they're very noisy. They're very noisy these days. So if you want to execute a quantum program, you want to make it as short as possible and compact. So you want to optimize it. And now we're going to use spiders to optimize this quantum circuit. So we know that the spiders of the same color fuse together. And you see there's two on the left and three in the middle. So they just fuse together. Now you see that the red and the green have two wires in between. So they fall away. They go away. Now you see, like on the left, I got like a wire, like a spider with 2 legs, but that's just a wire because spiders are the generalization of wire. Okay, so that goes away. So what we just saw and computed is that this circuit, which has depth 3, so that's 3 layers, can actually be simplified to a depth 1 circuit, and that the 3 CNOT gates actually correspond to simply having 1. So this is totally trivial. This is a totally trivial example, but as it turns out, using this spider trick, Frobenius algebras in monoidal categories, which is what it is in category theory lingo, this is now the state of the art of quantum circuit optimization. There is nothing better. There's no better way to simplify your quantum circuit than this method. This is now really the state of the art. And like big companies like Google and all that, they are now using these sort of tricks. Okay, so just to give an example, I'm not going to explain this because this is what you find in chapter 6. But for example, we prove quantum non-locality, which, as I say, is sort of the subject of the Nobel Prize this year. And basically, it boils down that this string diagram, which is something you can do in quantum, can never be represented by a string diagram of this kind, which is basically what people call hidden variable theories, local hidden variable theories. I'm not going to go into that, but this sort of advanced stuff you find in our children books. So they really get everything in there. Now, of course, it's a nice claim, like saying, okay, kids can do this, but we're actually trying to prove that too. So we're going to show that teenagers, and we're doing this now in collaboration with IBM, that teenagers using our new book and then learning quantum theory like that and getting an exam will outperform Oxford University students getting a normal quantum course and getting the same exam. So we're going to show that really this supposedly super difficult monoidal categories and Australian category and all theory as a la Kelly and all that actually enables children to do better with this language than Oxford University students with the normal quantum mechanical formalism. So that's what we are in process of working on. We haven't finished them, but this should soon be done. Now, this was the presentation as in our new book. So formally, the green and the red spiders and all of that is something called ZX calculus, which Ros Duncan and myself, Ros Duncan is now also in Quantinuum, he's the head of software, came up with in 2007. It was ZX calculus. And really what it was is the spiders, of course, trace back to Cartesian bicategories by Carboni and Walters. By the way, I was looking for mugshots of Aurelio and Bob, and I couldn't find them. So if anyone has them here, like nice mugshots, like the beautiful shot of Steve, of Aurelio and Bob, please send them to me because then I can use them in following talks. Now, it's good that I've got a paper here because you see, in this paper, we continue the program initiated by Ben Abu. So it's kind of it was definitely worth on this occasion to put this down. So basically, we use the spiders, the Frobenius algebras of Carboni and Walters. And then Steve studied interaction of these things in this, I think was it 2004 paper? I can't remember. But then we had to change it a little bit. We had to make them doubly interacting. Like, of course, Frobenius algebras themselves are sort of interacting monoids and comonoids. Bi-algebras are interacting monoids and comonoids. But we needed both of them. We needed interacting Frobenius algebras in a sort of bi-algebra way. And that changes the whole thing because, for example, every bi-algebra is then automatically a Hopf algebra, which is really important. And then we had to introduce phases just to make the language rich enough. So we had to do a little bit, but it all, again, traces back to these category theory papers. And now, okay, so ultimately, all this work and this diagrammatization or category theoretization of quantum mechanics is now used by at least all these companies in the context of doing quantum stuff. They may have been using it in another context. In the context of doing quantum stuff, all these companies are using this diagrammatic quantum stuff now in one way or another. And these are by no means all, because pretty much every week I discover a new one. Like this week I was giving a talk in Naples at the Italian Center for High Performance Computing, And then after my talk, a bunch of people come to me, yeah, we've been using this here for a while. And then the week before I was in Cannes, and then again, a bunch of people out of the field. So this is really becoming widespread now. So all this stuff is not anymore sort of just taking place in academia. It's really completely entering industry, both quantum and AI, and especially quantum AI. You see, quantum AI is the biggest chunk here. Like now, why is this language so powerful? Why is this ZX calculus, which is then based on the Frobenius algebras and all that, so powerful? Over a couple of years, a number of PhD students and also a team in Nancy, France, they, over a long period, have shown completeness with respect to Hilbert space. So this means that any equation you can derive using linear Hilbert space and linear maps and all of that, you can also now derive with these diagrammatic tools alone. So you don't need anything more. The diagrams of ZX calculus are now complete with respect to Hilbert space. And that, of course, shows why this language was so powerful. Now I'm going to completely change the story. Here is Jim. Jim, yeah, you remember Jim and Jean hanging out in Brussels in '99 at our workshop. So that's when I met first Jim Lambeck. I hadn't met him before. And I was in Montreal in 2005. I just had written this paper, Kindergarten Quantum Mechanics. And I was proudly explaining to the Montreal category theory group and category theory seminar, look, I've got these nice pictures of quantum theory. You can do quantum teleportation just by basically yanking wires and stuff like that. And then Jim was in the audience and said, Bob, this is grammar. Bob, this is grammar, he said. I said, no, Jim, this is quantum stuff. This is teleportation and quantum stuff. And Jim, no, Bob, this is grammar. And Jim was right, of course, because in the form of a sort of latest grammatical formalism, for those who don't know, like Jim wrote this paper, The Mathematics of Sentence Structure in 1956, I think, where he sort of formalized in a really nice way how we figure out that, or a machine can figure out that a sentence is actually grammatical. And in his latest incarnation in 1999, he basically came up with this thing called pre-groups, but they were really only post-settle non-symmetric compact closed categories. They were symmetric non-post-settle compact closed categories. So effectively, you had the same structure here with these diagrams as he had, like for his pre-groups. And I mean, I didn't take much notice at the time because I was mostly trying to diagrammatize quantum theory, but like at some point, a few colleagues in Oxford, there was Marnoush Chaudhry-Zadeh, she's now a professor at UCL, and she knew the grammar of mathematics, like I call it like that. Some people call it categorical grammar, but it's like the Lambeck thing from '99, the pre-groups, because Lambeck had asked her to do pre-groups for Persian, which she then did. So she knew about that stuff. And I mean, I don't know how much you have. I'm not going to go into details. I'm sure a lot of people of you know this. But basically, the key thing is that if you do a calculation in pre-groups, like a rewrite, which verifies that a sentence is grammatically correct, you can always draw a diagram like this, which represents the calculation. You can always draw a diagram using cups and plain white, which represent the calculation. I hear a big noise. Where is this coming from? I don't know. Okay. In any case, so remember this picture here at the bottom? So also at Oxford at the time was Steve Clark. Steve Clark was somebody who was quite early on doing what now all these big companies are doing, building GPT-3 and all these machine learning stuff using vector representations of meaning. So at that time, there had been no deep learning yet and all that. So vector representations of meaning were very much an academic discipline, and Steve was working with them. So you represent the meaning of a word by a vector. I'm not going to go into too much detail there, but what you got here is two representations of the mathematics of I think somebody has their microphone on. Am I right? They don't know. Okay, I'll speak louder. Okay, microphone off. Okay, good. So what we got here is two representations of, or two ingredients which are part of language, formalized. One is grammar using pre-groups, and one is meanings using vectors. Now, how do you bring the two together? How do you combine vector meanings of words with grammar? Now, the challenge here is, for example, we are able from the meaning of words and grammatical structure to derive the meaning of the sentence. There's still somebody running around and making a lot of noise, I think. Am I right? Okay. Okay. So the question is, how can we mathematically represent the process of what we do, like turning meanings of words using grammar into meanings of sentences? Because that's what we do, because we don't have dictionaries for sentences. And this is actually what's called Frege compositionality a la Frege. So basically the answer was given by Lambek pretty much, because in this diagrammatic formalism, we both at the structure of language in terms of grammar, and in the wires, vectors flow, because in quantum mechanics, vectors flow there. So we could use our categorical quantum mechanics formalism to combine meaning and grammar. So, which we did in this paper. I'll just show you how it kind of roughly works. So this is the algorithm which combines meaning of grammar. So what you got on the top are representations of meanings of words. So they're vectors, which we in our diagrammatic quantum formalism represent like that, like boxes. And what you see at the bottom was this diagram I showed you earlier for grammar. And so we basically use the grammar then to combine the meanings of words. And we did a lot of experiments, and it worked incredibly well, much better than anything else that was available. So it was generally a new theory. Well, the first one really of combining like vector-like meanings with grammatical structure. And then you can do things like computing inner products between sentences and see whether they're similar. Before they only could do this for words. I mean, I'm not going to go in details, but also the Frobenius algebras, the spiders, they play a key role in this new language theory we have. Also they play the key role in there. Now, like, I mean, here is an example. So this is spiders used to formulate a relative pronoun. So you can represent relative pronouns very naturally with spiders. So we got quite a little bit of attention there. But you know, at the time, I was telling Mernouche and Steve, never mention that this has anything to do with quantum, because otherwise we're going to be branded crackpots. If you do something like that, if you say something like that, language quantum, people are going to declare you crackpot. So we're trying to hide, but we failed, because all these magazines called us quantum linguists and blah, 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 blah. However, there was Feynman, who in 1982 or something said that if you got any theory which is quantum mechanical, then you're going to have a hard time putting this on classical computers, on traditional computers. And while our results were really good, once we started to try to scale them up to bigger things, we start to really struggle with computational power. Now today, or since a few years, we actually have quantum computers around. And so the natural question is, can we actually stick our new theory on quantum computers? So I've started to investigate this with Will Zheng, who's now the head of quantum at Goldman Sachs. You know, all these big banks, they have quantum entities now. So Will is the head at Goldman Sachs. And we investigated, like, if we stick all this quantum theory on a quantum computer, do we get a lot of advantage? And the answer was yes. So we get actually quantum advantage algorithmically. And in 2020, we effectively did quantum natural language processing on quantum computers. And this was really only possible because of this correspondence between, on the one hand, quantum theory and linguistic theory, using monoidal categories, using compact closed category, using Frobenius algebra and all that. So that's the fact that we could actually translate, and I'll show later very quickly how this works, linguistic structure into quantum computational circuit structure. We could translate linguistic structure in quantum computational circuit structure. We actually were doing a form of machine learning or AI, but where we actually used a lot more available structure, which usually now machine learning algorithms don't do. They don't do this because this structure is actually exponentially expensive, but on a quantum computer, it doesn't matter. It doesn't matter. So we did it on quantum computer, we did it bigger on quantum computer, and now you can do it yourself on quantum computers. We actually created this software called Lambec with a Q at the end, for obvious reason, like why we call it Lambec. And this is open source, so everybody can basically now do this quantum natural language on quantum computers. But there's actually quite a few quantum computers publicly available for playing around with for free. Queues are long to use them, but you can do it. So that's here. Cambridge Quantum makes quantum natural language processing a reality, and we basically gave it to the world. It was kind of interesting because I was in contact with Jim Lambec's family at the time, with his sons. And then they were very surprised because in this Forbes article, they mentioned Jim Lambec and his work. And said, the last thing I would ever see is my father being mentioned in Forbes. I think it was Michael Lambec who said that. Anyway, so now many other places are using this stuff, like IBM is now working hard on it. They're generating language using quantum computers and this diagrammatic monoidal category formalism. I'm going to skip a bit. I'm probably soon close to the end, so let me just let's end with something fun. So we basically took Lambec, the software, not Sam the person, of course, and we replaced the linguistic grammar with a musical grammar. These are things which exist. You can develop grammars for music. And so we created something which we called Quanthoven, a music software. And we started generating music with that. And one of our songs we generated became #1 in some classical charts. So one of the songs we generated on a real quantum computer, this was on a real quantum computer, using all this monoidal category theory, compact closed category, Frobenius algebra, formalism, basically became #1 in the classical chart. So if category theory led to anything, this is something. I mean, that's a joke, of course. So so inside Lambec, basically what happens is you start with a sentence, then you throw in some spiders, Frobenius algebras, and then using Frobenius algebra, so these correspond with two different colors of spiders, you sort of deform the thing, and you end up with something which is a quantum circuit that you can stick on a quantum computer. So that's what's happening inside Lambec. I'm sure if Lambec would still be alive, and I would be telling the story, this is happening inside Lambec, he would love it. I'm sure of it. Anyway, I'm just going to skip all the rest and just end here and here. So if you have more questions after the talk, you can also always ask them on Twitter. Actually, I also moved to Mastodon because I think most people, especially in category theory, applied category theory, are gradually all moving to Mastodon instead of Twitter. Okay, thank you. That's it.
Have you questions?
Can't hear anything.
Questions?
And I know who the noisy was. It was Noam. I see it.
Okay.
Anyway.
Is there a categoric traduction of the notion of entanglement?
Well, yeah, I mean, it's like the compact closed category. That's entanglement. But that's the simplest form of entanglement. Using the Frobenius algebras in ZX calculus, you can capture any kind of entanglement because this language is universal. So using Frobenius algebras, you can get a universal language for quantum computing, which means you can write down every matrix. You can draw down, and the completeness then says that any equation you can derive using linear algebra, you can derive using Frobenius algebras in the form of interacting Frobenius algebras, I should say, in the form of ZX calculus. And that's now being used widespread in quantum industry.
Other questions? I think that we can pause lunch. Donc, il est maintenant 12h45. Personne pose de questions. Nous avons un cerveau, mais nous avons aussi un estomac. Donc, je suggère qu'on fasse la pause déjeuner et on se retrouve à 14h.
Okay.
Thanks a lot, everybody, for attending. I'll keep the Zoom session open. I'll stop the recording, and it's the same link if you want to come again at the meeting after your lunch break. Thanks, and see you soon.
Et Isar,
Oui.
tu fais un seul enregistrement par demi-journée ou tu fais les enregistrements par intervention?
Ben, en fait, je dois dire que je ne sais pas très bien, c'est Zoom qui fait tout automatiquement. Donc là, je vais juste, je pense, mettre en pause l'enregistrement. Et après, j'ai compris que ça m'envoie un lien pour télécharger l'enregistrement. Et je vais demander d'abord aux orateurs par mail s'ils sont d'accord pour diffuser ou pas. Mais je vais sans doute te demander un coup de main parce que moi, je suis absolument nul pour ça.
On fera ce qu'on pourra. OK.
D'accord?
OK. Bon appétit à tous.
Bon appétit, à bientôt. À tout à l'heure.
Hello.
Hi, is this Frederick Quintana speaking?
Yes.
I think Bob is still around in the meeting, so you can ask your question.
Okay.
I think that the moderator did not see your raised hand.
I was
I'm here.
Hello, Bob. I was wondering if any work has been done relating QNLP to the problem of polysemy in lexical semantics, for representing this alternative senses of meaning. So,
yeah. So, I mean, that was one of the things, and this was before it was QNLP. This was when we were just doing things with on classical machines. That was one of the most, the earliest things which Marnish was at then, Marnish Sadrzadeh and some other collaborators were doing, like disambiguation. And that's where they actually got really, really nice results. Now this is one way, that's what actually, at first the theory was shown to be very, very useful. The problem was we had a scaling problem. And then of course you need to do it on quantum computer, but we are now also doing some disambiguation experiments on quantum computers. There is another thing, trouwens, that's Flemish. One thing quantum mechanics gives you too is a nice representation of ambiguity, which is von Neumann's density matrices. Because von Neumann introduced density matrices when you have ambiguity on the quantum state, which is the same, of course, of ambiguity on meaning. And Martha Lewis has done a lot of work using this formalism and using density matrices for ambiguity in language again in general. There are some really nice things we see then is, for example, you've got a very ambiguous word, which is ambiguous on its own, like a word like queen, which can have many meanings, can be a bee, can be a chess piece, can be lots of different stuff. And then when you start composing it with different words in this formalism, then the ambiguity goes away, which is kind of at least conceptually, a very nice thing to see happening.
I'm not sure if it's the appropriate, I guess, tools from a quantum toolkit, but I was thinking of some kind of database for lexical semantics where the specification of individual senses are some kind of sequential composition, and the alternative senses are parallel composition, and it somehow draws on a common pool of nodes for the terms used in specifying each sense. Does that sound like anything people are working on in terms of ambiguity for, I guess, specific words in context?
Yeah. I mean, so here is a very interesting feature. Which makes the quantum experiments very different from the classical experiments. Like the quantum experiments, and this is due to the nature of the current state of the art of quantum technology, is that the way we actually get data in the circuits of the quantum computer is not by basically just encoding classical data as qubits, because that's inefficient. That one would need something that's called QRAM, and that doesn't exist yet. People haven't sort of built it yet. So the way now data is sort of put into a quantum computer is you train circuits. And so inside the circuits, you got these different meanings of things which make up a sentence or a text. So they're automatically trained within context, the words. So what you were just talking about seems to be a very interesting way to actually sort of get ambiguous words into the system, because training within context is basically what we already do.
Mm-hmm.
Does that make sense?
Yes, thank you. Well, the term training is, of course, also used in deep learning.
It's the same. It's the same. It's really the same. Like,
well, my fear is, how much data do you need? Can this be done with small?
Good, very good question. This is the best question you could have asked. So we do training, but we need a lot less data because we're using structure. Like normally in deep learning and all that, you have to learn the grammar. Grammar is a very complicated beast. So we don't have to learn the grammar. So because the grammar is actually the structure of the circuit over we train. And that makes it much cheaper, because I can tell you the quantum computers on which we did this in 2020 were really small. And we were able to get actually good results because, of course, like a qubit is a continuous entity, so you can actually store quite a bit in it. It's not that just not quite a bit, as in not just one bit, but quite a lot of stuff. And so we're doing this on small quantum computers, and the advantage really comes from the fact that the circuit over which we train takes account from the linguistic structure, which in machine learning, you just have to learn from scratch. Does that make sense?
Yes, it does. So what is the limit? How come language models have a hard time squeezing into small quantum computers that are available today? What is it
would be
that
impossible.
makes...
It would be impossible. You like standard machine learning couldn't be linguistic NLP couldn't be done on a quantum computer at the moment. It just couldn't, because of exactly what you said. Too much data.
So I know that, for example, Ty Danae Bradley has been working on, I guess, large language models in relation to, I guess, linear algebra and quantum approaches to linear algebra.
Well, I mean, what Ty is mainly using is what I mentioned earlier, are von Neumann's density matrices to represent certain things. Yes. In different way. So, but it's not quantum. This sort of thing wouldn't naturally fit on a quantum computer in the way they are doing it. They're using basically a piece of quantum mathematics, or mathematics which was introduced in the context of quantum mechanics, like for ambiguity on quantum states, which I mentioned earlier, density matrices, and they're using this to encode certain concepts. Which is a natural thing to do. Actually, I think it's very natural what they're doing, but it's not the sort of thing that naturally fits on a quantum computer. So it's a different thing. You're really using the structure of density matrix to get a bit more structure in play. So to that extent, it's similar.
So I guess my hope is to move away from large language models to an approach to specifying individual lexical items as an alternation of small senses. So small networks rather than a large language model. Yeah, and hopefully small enough that it could be loaded into quantum circuits that are available today.
So I mean, some of the things we are doing now there is something I didn't mention in talk. So we moved like beyond DiscoCat to sort of new theory, which is actually much more economic in many reasons, and it extends from sentence to text. And we call it DiscoCirc. There are many papers. There's only one paper out there by myself, the mathematics of text structure. And we've been doing experiments on tasks which usually large language models are quite good at. They're good at, sometimes even perfect. But of course, they need a huge amount of data and space and processing power. And we are doing exactly the same with this new theory on classical computers. There's no papers out, so we're starting to write this down, but that's exactly what we're seeing. We see resource reduction. And of course, the reason is that given the structure we use, I mean, I don't know whether it's the right word, but I mean, I can't really come up with a better one. The model is more aware about meanings than a large language model would be.
Mm-hmm.
You understand what I'm saying? And therefore, you can do things much cheaper. And of course, then the next stage is to show that things large language model completely fail at, because they still fail at a lot of stuff. Like if some people, their jobs is just coming up with things where they radically fail, then showing that you actually can also attack these sort of things. I mean, I don't know whether you're aware, but like we only started to do this 2 years ago, so it's all very recent stuff.
I think I saw the name of Dimitris Kartsakalis.
Yeah, he's working with.
So, is this the group? Okay.
He's the lead developer of Lambic. No, when I'm saying we started to do this 2 years, is actually taking quantum serious.
Mm-hmm.
And part of the problem is like in academia, at least in my case, the activity on this had sort of fallen down, because in academia you can't compete with like large language model industry. You need a little bit more resources. That's part of the reason I actually moved to industry, because something like this would be virtually impossible to do in academia, like taking up the large language models.
I wonder if any of this area of work might have implications for the opaqueness of deep learning, which I think also characterizes large language models, and
Well,
whether it might help to introduce small representations of structure, so that instead of constantly dealing with the global range of variation, you can just trigger a smaller set of representations triggered by the words that actually occur in the utterance you're currently processing.
Well, to some extent, that's the sort of the things we are now really doing. Like, but you're right. So yeah, to go back, yeah. So Dimitri was actually my PhD student too, and he was one of the first PhD students who worked on this DiscoCat stuff. But like I said, at the time we weren't sort of considering all the quantum things yet, and the resources were much harder to get, and so things didn't move. So Steve Clark then moved away to Cambridge, stopped doing all this stuff, then went to DeepMind, and now is full on in the quantum stuff back. And Dimitri also came back from Apple. He went to Apple and then came back here with us now. So we're kind of all reunited from like around a little bit more over 10 years ago.
Is there any contact with the group at Gothenburg University, which
very interesting question. Very interesting question.
Have a center.
So Steve got just invited. He was by jointly Gothenburg and Chalmers jointly to basically get a course there. A course. I mean, it's going to be a joint course. I'm going to be part of that too. A joint course. And also a workshop and a school specifically on what we do.
Huh.
So this is going to happen.
Sounds very interesting.
That's going to happen soon. So I mean, I haven't directly. I mean, I know Shalom Lapin. I've met him a few times years ago. So I've known him quite well for a while. And so yeah, so we're definitely going to. And then the plan is also to see how we can collaborate and all that. So this is going to be happening somewhere in spring. Are you connected to them?
Not directly. I've corresponded, but no.
Okay. So yeah, so there will be definitely a connection.
What I find interesting in their work at Gothenburg is, or one thing I find interesting, has to do with dialogue and discourse. And again, because I hope there's a way to incorporate some insights from not so much the grammatical side, but more, I guess, a tradition in what's called situation semantics, which how do I describe this? Yeah, anyway, so people like Robin Cooper, who work closely with the originators of situation semantics, has been trying to come up with a implementable model of dialogue. And I think that my ideas about lexical semantics could fit into discourse by interfacing with that model.
Okay, I see. That's interesting. I see. Yeah, I mean, my guess is that the thing I mentioned, this disco-circ driven, our new formalism is much closer to this sort of stuff. But we'll need to figure it out. Again, this is so recent that there is no papers even on it out there.
Okay.
So it's. I mean, yeah, like I said, I mean, I spent a lot of time writing these books and, and all that. Like, so I wasn't really, for a long time, this was just a hobby for me, this language side. Like, but now it's becoming quite a bit serious. And also Marnouche now has an institute at UCL specifically for this, and a big grant together with us and BBC and all that. So the activity is seriously going up now. And I mean, it's remarkably how many companies are using Lambec now and playing around with it.
I wonder, perhaps going beyond the NLP dimension, whether I guess especially the situation semantics tradition I mentioned has also produced some ideas about information flow in general, but still retaining applicability to natural language. So information flow in this case would be modeled in terms of, I guess, Barwise and Seligman talk about, I guess, applying true constructions. So star autonomous categories and so doing so in a way which could, at least in theory or in principle, encompass this tradition of situation semantics that Barwise was heavily involved with. Unfortunately, he died too early.
Yeah, I know. I mean, I was colleagues with Alexander Baltak, who was like a student of Barwise. So and I know this Barwise and I mean, I knew it like more than 20 years ago, but it's been a while. But so one thing we are now doing in collaboration with a number of people is, I mean, I mentioned during my talk like Frege compositionality, but it's a very limited form of compositionality where like from the small you get the big. It's a very naive way of information flow, and we are now trying to really mathematically characterize like the landscape of possible information flows to account for things like the quantum case and the linguistic case, where the context is much more involved and a lot of meaning flows top down, not just bottom up, which is really what's also happening with neural nets and deep learning. Really, it's like you train top down, and to understand this mathematically, and it's not totally trivial. It's not totally trivial, but that's I think the first step in that direction, to sort of take a more modern view on this different. And actually, it's good you point out again the Barwise and Seligman thing, because I kind of forgot about that for a while. That was mainly.
I think much more recent work on by the group of John Baez, working with people like Michael Schulman, who is active in the homotopy type theory community. They've come up with a paper about Petri nets and trying to generalize them that makes use of pretty much the same true construction, although he talks about two categories rather than the one categorical approach used by Barwise and Seligman.
That work I'm very well aware of. Like, I mean, one person who's involved in what we're doing now is Fabrizio Genovese, who worked on that stuff specifically. So he's in our team, and then Amara Ziazanovic is also in our little, and then Katerina Pucci, who was here in the. So we got a little, and Jules Hedges. So we're trying to establish.
Yes, I know Jules as well as Fabrizio.
So we're trying. That's kind of our team. That's kind of our team where we're trying to nail down what compositionality actually means in its broadest form. And that's the first, and that of course goes in the direction of information flow and all that. So again, that's ongoing just now. So anyway, I think I have lunch because I've got a meeting.
Sorry.
No worries. It was nice. I just clicked you to follow on Twitter.
Okay.
So we can stay in contact there.
Yeah, I also started on Mastodon. So
okay. I'll look for there too. Anyway, I have to go now. Bye.
Okay. Thank you for your time.
Cheers.
Cheers.